Hello again, ladies and gentlemen. Mr. Donnie here, looking to go over some chemistry problems with you. Looking at chapter 6.7, 8, and 9. I'm going to do them all in one foul swoop. All right, so we are starting with question 28. At maximum, an F subshell can hold blank, and D subshell blank, and P subshell blank. So S, we get one orbital box, so you can get 2 electrons in that. The P, you get 3 boxes, 2 in each, so you got a total of 6. The D, you get 1, 2, 3, 4, 5 boxes, so you get a total of 10. And the F, you have 7 boxes, 1, 2, 3, 4, 5, 6, so you get a total of 14. So the 1 will be 14 for the F, 10 for the D, and 6 for the B. So choice A. All right, which electron configuration represents a violation of the Pauli exclusion principle? It's specifying which one is it's violating that rule, which says that there can be an up and a down in the same box, but you cannot have 2 of the same spins. You can't have 2 ups, or you can't have 2 downs. Can't happen. So which one's violating that? Well, let's take a look. This one is incorrect, but it's not incorrect for that reason. It's violating Hund's rule, which says that every box should get 1, every orbital should get 1 electron before you pair any of them up. There's nothing wrong with B. C, here's the issue right there. You can't have 2 electrons with the same spin in the same box. You can't have all 4 quantum numbers be the same. For choice D, this is fine, but, you know, convention says we usually would have put the arrow in this box instead of that one. They're the same energies and stuff. You just seldom see it written that way. And E is fine too, except that is something in the excited state. Right? It's not violating Pauli exclusion principle. All right. 30. Which one of the following represents an acceptable set of quantum numbers for an electron and an atom? And are arranged as follows. So we got to remember that we got N, L, ML, and MS. So N is any whole number. L can be anywhere from 0 up to N minus 1. ML can go from negative L to positive L. And MS is either plus or minus 1/2. For the spin of the electrons. Which one of these is possible? Well, this one's not possible because that's saying you're in the 2D sublevel, which doesn't exist, so it can't be A. All right, B is looking good. Let's skip and come back for a second. This is what's wrong with that one. With C, you're saying you're in the 3, 0 is S, 1 is P, D is 2, and 3F, which doesn't exist. You can't have that. For 5, we can't have a negative 5 for our ML if our L is only 4, so that's not possible. And E, we can't have 3, F sublevel, so that's not possible. Choice B is the only one that is possible. 31, which of the following represents an acceptable possible set of quantum numbers? Like this last one, but different options. Right? We can't have a 0 spin, so we know it can't be B. We can't have a 2D sublevel because that doesn't exist. We can't have this be 1 if it's 0 for the L. It would have to be 0, right? And for E, it can't be, again, you're saying it's 2S, you'd have 1 box, and that 2 is saying that you're in, well, if this is 0, the next non-existent box would be 1, and the one after that would be 2. You can't have that. So choice A is the only acceptable one. All right, so which of the following is the correct electron configuration for the ground state of the nitrogen atom? Nitrogen atom, you can look up its configuration. It's 2-5, which means it'd be 1s2, 2s2, 2p3. All right, 1 box, up, down. Another 1 box, up, down. And 2p would get 3 boxes. You got to remember, ground state, you follow Hund's rule. Everyone gets an arrow before you go back and pair anything up. So it should look exactly like that, which is choice C. All right, you got to watch out for this. That's not right. You can't have two ups, right? This should be in another box, so that's not right. Violating Hund's rule there. Oh, crap. I'm sorry. Wrong problem later. You can't have C because you got two up there. That ain't right. But D is correct. This is the correct answer. All right. 33. Which electron configuration is a violation of Hund's rule for an atom in the ground state? So remember, Hund's rule is everybody gets one before anybody gets two. All right. This is an excited state. Mr. Donahue, how did you know? Because if you had only 3 electrons, you should have the 1s full, but you promoted one of those electrons to the 2s, so it went up in energy level. That's fine, it's just not the ground state. This right here is incorrect, but not for Hund's rule. That's a Pauli exclusion issue there. C, well, let's see. That looks like it's a violation of Hund's rule. That arrow should have gone in another box. So C's looking good. Let's take a look at D though. This is actually, like I said before, fine, but you won't really see it. Convention says that we would put it in this middle box instead of this end box. So it's not a violation. It's fine. And then E is the actual, there's no violations here. So we're looking for a violation. Violation would be C. 34. Ground state electron configuration of the element blank is Kr bracket 5s1 4d5. Now the easiest way to do this would probably go, well, I know Kr has 36 electrons plus 6 more equals 42. So you go, all right, well, what element would have 42 electrons? The element that had 42 protons. Atomic number of 42 would be MO. Right. Similar but different. This is the electron configuration of blank atom. I do the same thing. Look up Ar as 18 electrons plus what's the total of this? 15. So what element would have 33 electrons? One that would have 33 protons. Atomic number of 33, Ks. Ground state configuration for fluorine is blank. Well, I know it's 2-7. So I know it's 1s2, 2s2, 2p5. And I know that this 1s2 is helium. So helium, 2s2, 2p5, choice D. All right, 6.9. How many different principal quantum numbers, aka energy levels, can be found in the ground state electron configuration of nickel? Well, you just kind of look up nickel, see what period it's in. It's in period 4, and that's saying that there's 4 principal energy levels, so you have 4 principal quantum numbers. Choice C. 38, all of the blank have a valence shell electron configuration of ns1. So, well, it would be like 1s1 or 2s1, 3s1. You have 1 valence electron. So what group has 1 valence electron? Group 1. Special name for group 1 would be the alkali metals. 39. The elements in blank period of the periodic table have a core electron configuration that is the same as neon. Well, neon is 2-8. Right? So it's saying all of them are 2-8 something. So that tells us we got 3 principal energy levels. So it would have to be in the 3rd period. That's it. You got a test coming up. Hope you've been studying. Hope you found this helpful. Hope you're ready for it. See you in class.